Hello. I'm going to present my work titled Synthesis and Characterization of MoS2 Nanoparticles by Laser Fragmentation in Liquid Phase. Molybdenum disulfide, MoS2, is a 2D semiconductor in the family of the transition metal dichalcogenides, TMDC, which has an indirect energy band gap in bulk of 1.4 electron volts that can be changed into a direct band gap of 1.9 electron volts when working with thin films of the material. When working with nanoparticles of MoS2, the energy band gap of the material presents a blue shift due to quantum confinement that depends on the size of the nanoparticle, which makes MoS2 nanoparticles a good candidate for devices of light detection, LEDs, biomarkers, etc. To synthesize nanoparticles, laser fragmentation in liquid phase, LFL, is a useful technique due to its high stoichiometry conservation and easy management of the parameters used during the process, which lead to an easy control over the size of the nanoparticle one wishes to obtain. LFL is a technique in which a high-energy density pulse laser hits a micrometric powder of the target, which is suspended in a specific solvent, leading to the formation of nanoparticles of the target inside the liquid media. When hit by the photons from the laser, the target gets ionized, creating a small plasma inside the solution. This in consequence generates a big temperature gradient between the plasma and the liquid media, delimited by a small vapor layer of the solvent, called the cavitation bubble. Inside of the cavitation bubble, nanoparticles of the target are being generated, and because of the temperature gradient, this bubble tends to expand until it breaks, releasing the nanoparticles into the solvent. For this work, an ND-YAG pulsed laser with a frequency of 50 Hz was used. 6 different syntheses were made, varying only in the solvent used. The 6 solvents used for this work were methanol, ethanol, 2-propanol, acetone, distilled water, and deionized water. It was observed that right after the synthesis, all samples were completely black, which is to be expected because of the characteristics of the bulk MoS2. However, as time went by and the heavier particles sunk to the bottom of the container, the samples started to present different colors. Some of them turned translucent while others presented a blue tone. First, through scanning electron microscopy, SEM, it was observed that all samples presented nanoparticles of MoS2, ranging from 90 to 900 nanometers depending on the solvent. Another very interesting result obtained in the SEM images is that all samples presented bigger triangle-shaped MoS2 particles that appear to be formed by the conglomeration of the sphere-shaped nanoparticles. This could be because of the 2D nature of the material as well as its preferential hexagonal structure. Another characterization made was X-ray diffraction, in which all samples presented the main peak of MoS2 in its hexagonal structure, located at around 14.5 degrees in the 2 theta configuration, corresponding to the diffraction plane 002. Other peaks corresponding to this structure were observed in all samples, confirming the presence of crystal MoS2 nanoparticles in its hexagonal phase. There were also other peaks present that do not correspond to MoS2 nanoparticles, which are yet to be identified, as well as one specific peak located at around 23 degrees in the samples corresponding to distilled and deionized water, which could be due to molybdenum oxides generated by the interaction between the water and the MoS2 nanoparticles. The next characterization made was UV vis absorption spectroscopy. For this characterization, a measurement of the time evolution of the samples was made, measuring each sample every 2 to 3 days for 2 months. The main change presented in time for all samples were the increase in the transmission spectra due to the heavier particles settling. After the 2 months passed, there was a clear absorption band in all samples, ranging between 300 and 450 nanometers, corresponding to the energy band gap of the material. With these spectra, the derivative of the optic density was calculated to obtain the energy band gap of each sample, which varied from 2.8 to 3.8 electron volts depending on the solvent used during the synthesis. In all cases, we observed a strong blue shift in the energy band gap with respect to the bulk material or even thin films of the material, this being a consequence of the quantum confinement that nanoparticles present. Photoluminescence spectroscopy was also measured. All samples presented photoluminescence, which is to be expected due to the shift from indirect to direct band gap of the material when reducing its dimension. The main emission bands observed in the samples are above an energy of around 2.3 electron volts, which corresponds to a blue light emission. The different positions of the emission bands in the samples are mainly attributed to the different size of nanoparticles obtained during the synthesis because of the variation of the solvents used, and can be confirmed by the SEM images showing a wide range of sizes obtained. Finally, Raman spectroscopy was measured. All samples presented the 2 main characteristic peaks of MoS2, located at around 380 and 400 centimeters -1, which correspond to the two main vibrational modes of a 2D structure, the first being attributed to the in-plane vibrations of molybdenum and sulfur and the second due to out-plane vibrations. Aside from these modes, there was also another mode observed denoted by 2La, located at around 454 centimeters minus 1. The rest of the peaks observed in all samples correspond to combinations of these modes. In conclusion, hexagonal nanoparticles of MoS2 were obtained through laser fragmentation in liquids for all samples. The size of the nanoparticles obtained varied from 90 to 900 nanometers, which in turn affected the different optical properties such as the emission and absorption spectra of each sample in different ways. Bigger triangle-shaped particles of micrometer size were also obtained probably after the synthesis of the nanoparticles and during the sedimentation process of the samples, since these triangle-shaped MoS2 particles appear to be made from conglomerations of the smaller sphere-shaped nanoparticles. These differences give rise to a further study of this nanomaterial under different growing conditions. Thank you for your attention.